Here's a review problem on fluid statics. It's from the AP Level B exam from the year 2014. This is problem number 2, and this one has to do with buoyant force. So we're told that a cube with a mass of m and sides of length L is completely submerged as shown in this picture. The tension in the string is 0.25 times the weight of the cube. The density of water is given as 1,000 kilograms per cubic meter. Part 1, draw a free body diagram. Show all the forces that act on the cube. Each force must be represented by a distinct arrow. Okay, so how many forces are there? I believe there are 3 forces. We can't get away from the fact that the cube weighs something. So there's a downward force we can represent as mg, and then we're told there's some tension in the string. And if we draw it to the scale, the tension is 1/4 of the weight. So I tried to make that vector about 1/4 as long as the green vector. Okay, so this doesn't represent equilibrium. There's got to be another force. And of course, the other force that balances everything out is the buoyant force. So there you have it, buoyant force, tension, and gravity. And from this, we need to calculate what's the density of the cube. So let's see if we can express equilibrium. Step 1, we can say buoyant force is equal to tension plus mg. The tension we're given is mg over 4, 0.25 times the weight of the cube. So mg over 4 plus mg, so this gives us 5/4 mg for the buoyant force. But buoyant force is equal to density of the fluid times gravity times the volume of the fluid. Well, in this case, if the cube is fully submerged, then the volume of the fluid displaced is the same as the volume of the cube. Okay. So we get density of fluid times g times volume of the cube is equal to 5/4 mg. Now what are we trying to solve for? We're trying to solve for the density of the cube. The mass of the cube should be equal to the density of the cube times the volume of the cube. Okay, so this is 5/4 density of cube, volume of cube times g. So look at everything that cancels out. G cancels out, but so does the volume of the cube. What we're saying is the volume of the cube and the volume of the fluid are equal because it's fully submerged. So the density of the fluid is equal to 5/4 the density of the cube. So that can be expressed as the density of the cube is equal to 4/5 the density of the fluid. The fluid, we're told, is water, and water has a density of 1,000 kilograms per cubic meter. So we get our final answer. The density of the cube is equal to 800 kilograms per cubic meter, right? 4/5 of 1,000. Okay. Now we're told in part C that the string is suddenly cut. We need to calculate the magnitude of the acceleration of the cube immediately after the string is cut. So if we cut this string, then this one force goes away. Tension is now gone. But we still maintain the same amount of buoyant force because the cube is still fully submerged. And of course the weight doesn't change at all, right? So now there's a net force, and that net force would be the difference between the upward buoyant force and the downward force of gravity. So we can say ma is equal to buoyant force minus mg, or A is equal to buoyant force divided by mass minus g. And the buoyant force is equal to the density of the water times gravity times the volume of the water. and the mass is the mass of the cube is the density of the cube times the volume of the cube. But the volume of the water and the volume of the cube are equal volumes, so that cancels out. So we get acceleration is just g times the density of water over the density of the cube minus 1. So we get acceleration is equal to 9.8 meters per second squared times 1,000 over 800 minus 1. But 1,000 over 800 is the same thing as 5/4. So we get A is equal to 9.8 meters per second squared times 5/4 minus 4/4, or in other words, the acceleration is just equal to 1/4 g, which is equal to 2.45 meters per second squared. Let me clear some room. Last part. Indicate whether the magnitude of the buoyant force on the cube increases, decreases, or remains the same while the cube is rising. So we draw the cube here at point 1, and it accelerates upward. So now the cube gets to this point, it reaches this point. What would the buoyant force be at each of these positions? Well, buoyant force is just equal to density of the fluid times gravity times the volume of fluid displaced. And as it rises, it continues to displace the same volume of fluid. The density of fluid, it remains 1,000 kilograms per cubic meter. So there should be no change in the buoyant force, and that ensures that this acceleration is a uniform acceleration.